We've been looking at quadratics, and we've been looking at several different ways to solve quadratics. So now we need to talk about how to decide which method to use and when. The first kind of quadratic we'll look at is when you have a quadratic equation when there's no bx. And when you have that, the best way to solve this kind of quadratic is just using SADMAP, right? To work backwards through the order of operations. To get rid of the 36 first. To get rid of the 4 next. And to get rid of the square root last. Always remember that when you take the square root, you need to do both the positive and the negative square roots. The second way to solve quadratics, again, not our favorite way, is to graph it. We know that this is the most time-consuming and least accurate of all methods, but it's still possible. So in a really abbreviated way, I've already sort of done the work to get us to the point of knowing where our axis of symmetry is and what points our first 5 points would be. Let's take a closer look. So when we look closer at the graph and graph the points, we can see these 5 points are all below the x-axis. Let's go ahead and start drawing in the curve. And as we draw in the curve, we get to some point around there and here. And that's what we know accurately. We now want to take a look at the equation, right? And the big question is where is it 0? So when it crosses the x-axis. So when we go back, what we're really interested in is where it crosses the x-axis. Well, I don't know enough information yet, so I would need to do more work. Going one more point over, I can see that the next point I'm interested in is 1, 3, which is right here. And if I do a mirror image on the other side, I get another point here. Extending the lines, and now have 2 points where they cross. They cross here and here. So those are going to be my solutions. Well, I have a problem. I don't know exactly what points those are. Is that a half, 3/4, 2/3, an irrational number? Graphing, it takes forever, and yet there's still no guarantee that we're going to have a very accurate answer. So while you get a great picture of it, it's not going to be necessarily an accurate way to find a solution. Which brings us to the last 2 methods that we've learned about solving quadratics. We're going to want to have a kind of solution that we can do algebraically and not graphically that allows us to solve a kind of equation where there is a bx. We already have an algebraic solution for without a bx, but now we need one for with a bx. So our 2 options are the quadratic formula and factoring. Well, there's benefits and detriments to both. The first, right, so for the quadratic formula is that it takes time, right? It's very detail oriented. There's a lot of room for error. But on the other hand, it always works. Factoring, on the other hand, does not always work. The benefit to factoring is it can be quick. It can be fewer steps, fewer details to worry about. And if you see the pattern right away, it can be something that you can do in just a matter of a few seconds. So how do we decide? Well, here's the official answer. If the discriminant, that is b squared minus 4ac, is a perfect square, then the equation is factorable. So we want to be able to take a look at the discriminant yet again. So the discriminant tells us a lot. We've already learned that it tells us whether or not it has a solution. 1 solution, 2 solutions, or no solutions. Well, in this case, it's also going to tell us whether or not we can factor. So there's our a, b, and our c, and we can write out our b squared minus 4ac. Okay, so let's go figure out what this is. So 7 squared is 49 minus, right? Actually, I'm going to turn this into a plus negative, so I don't have to worry about it anymore. So it's plus, now it's a negative 4 times a 2 times a negative 10. So negative 4 times negative 2 is negative 8 times negative 10 would be positive 80. I add those together, I get 129. So, what does this tell me? Well, it tells me that this is not factorable. It's not a perfect square. So if it's not a perfect square, then there's no combination of integers that we could put together where we could set out a binomial factorization. It's not possible. So let's take a look at this one. 6x squared minus 5x minus 21 is equal to 0. So let's find our a, our b, and our c. And let's figure out whether this is factorable. So a is 6, b is negative 5, and c is negative 21. Our b squared would be negative 5 squared minus or plus negative 4 times a times negative or times c. 25 plus 24 times 21. Positive. I just did the negative times the negative to get the positive. (25) plus 24 times 21, that's 504, is 529. Well, 529 is a perfect square. If we take the square root of that, we get 23. So 529 is a perfect square. This is factorable, which means that there is a binomial factorization that we could get by splitting these apart into parentheses. Okay, so I hope at this point you've realized that there's a big problem here with the way to figure out how to do this. If you go ahead and find the discriminant, and the discriminant says that it's not a perfect square, you would use the quadratic formula. And if you've already found the discriminant, you're halfway there to being done. Which brings up the difficulty. If you do the discriminant and you find that it is factorable, well, what do? Do you go back and start from the beginning to factor, or because you've already done half of the quadratic formula, do you just continue on and use the quadratic formula? It seems a little silly, right, to figure out that this is factorable, but to already have the b squared minus 4ac, all you would have left to do would be this part of the quadratic formula, which really is not that much left to do. So why go back and factor? So we've realized that the official method of finding out whether it's factorable, the b squared minus 4ac, might not be the best way after all. So what do we really do? Well, here's my sort of gut feeling to tell you. If you see a quadratic equation where there seems to be quite a few options, right? So 6 has 2 sets of options, 21 has 2 sets of options. It's not that many, but you're going to have to go through a few. You have sort of a choice. You can either try factoring and hope you get lucky and maybe it's factorable and maybe you get that right away, or you can sort of head toward the quadratic formula. By the time you actually get to the right combination of factoring, if it's factorable, you might have been able to do the quadratic formula anyways. Now, you have sort of a simpler one. Maybe it's just an x squared, there's no coefficient there, there's not that many factors here. Maybe you see already the combination of factors that can get you to 9. Well, in that case, try factoring, right? If there aren't that many options, maybe you can get there quickly and save yourself some time. And even if you don't have an equation that's factorable, even if it looks factorable, something like this, even if you try a few options factoring, you're not going to waste a lot of time, right? There aren't that many options. You have to have a plus and a minus. The only options for 8 are 1 and 8, 2 and 4, and if you sort of do that quickly, right, you're going to be subtracting to get to 3. Well, the 1 and 8 doesn't work, and the 2 and 4 doesn't work. Okay, I haven't wasted that much time before I go on to the quadratic formula. So a little bit of this is sort of your instinct telling you what to do. If you really want to know whether it's factorable, then you use the discriminant. Okay, with all that said, I'm going to have you check out to see whether these are factorable. So these are going to be your practice problems. Do these, check them out, and then we'll see if they're factorable. Again, you're going to just use the discriminant. Okay, let's give these a shot. So let's take a look at this first one. Here's our A, our B, and our C. So our B squared minus 4AC is going to look like this. 34 squared plus negative 4 times 24 times negative 45. That's 1,156 plus, why did I choose such large numbers? I should have chose something a little simpler perhaps, plus 4,320. So our total is 5,476. So if we take the square root of that, we get 74. Well, that means it's a perfect square. So this is, in fact, factorable. For our second one, our A, B, and C are 1, negative 7, and negative 20. We'll do B squared, which is negative 7 squared plus negative 4 times 1 times negative 20. Negative 7 squared is 49 plus, and then a negative and a negative will be 80. That sum is 129. It's not a perfect square. It's an irrational number, so therefore it's not factorable. Last one, our A, B, and C are 2, 9, and 7. So when we do B squared minus 4AC here, we're going to have 9 squared minus 4 times 2 times 7. 81 minus 8 times 7, 56, and that's 25. So 25 is a perfect square. Right? Square root of 25 is 5. So this means it's factorable. And if it's factorable, right, we have a choice of doing the quadratic formula or factoring. And this is one of those strange cases where actually you might decide to factor this. Right? There's only one option for 2x squared. 2x and x. And there's only one option for 7. 7 and 1. So even though we've already done part of the quadratic formula and we found the discriminant, it would not be unreasonable in this case to go back and factor it. I could probably do that a little bit faster than finishing up the quadratic formula.